lot of things I like about pi, but one that kind of stands out. And so I thought I'd put it together into a little talk. I may not cover your favorite thing about pi, and since the talk only takes about a half hour, there'd be time for other people to give their own talk, my favorite thing about pi, before we leave. One thing about pi, which is kind of what we were just talking about, is that it's pronounced the same as the word pi. So, for example, what does this shirt say? Somebody louder so everybody can hear?
I ate some pie.
I ate some pie. Okay, so there's a nice nerdy math pun for us there. People think it's funny. I think it's cute. It's a cute shirt. I learned, however, that Greek people don't pronounce this symbol pi. When they see it, they call it p. It's their letter p, and they say p. They don't say pi. And I think since it's a Greek letter, they're kind of in charge of what it's called. So as far as I'm concerned, that technically is p. And I don't like that joke as much when it says I ate some p. So that's why, though that's an interesting thing about pi, and it's an excuse to eat pie, it's not my favorite thing about pi. So now on to something mathematical at least. So pi can be defined as the ratio of the circumference to the diameter of a circle. I promise those were circles on my computer. They look a little squashed now. I'm sorry, that's something the projector is doing. And I guess the thing that's interesting about that is the any part, right? Because if you said you've got some object and you measure two things, the ratio, that's not so exciting. The thing is that it doesn't matter which circle you're talking about. It's the same for any circle. In other words, it's a constant. Is that a surprising thing? Some people think so. In fact, I keep getting emails. Maybe the other professors in the room can tell me if they get the same ones. About twice a year, I get email from somebody who insists that it's not a constant. I've stopped reading or answering those emails. To me, it's kind of obvious that it is. So I don't really think this is that interesting a fact. It comes from two things. The first one is that if you've got a circle, you can scale it to make it the same as any other circle. You can't do that with triangles. If you have two triangles, you can't necessarily scale one of them and make it look the same as the other. I guess this is the statement that any circle is congruent to any other. And the other fact is that if you scale it, both the diameter and the circumference are going to scale by the same amount because they're both measured in the same units of distance. Put those two things together and you get this conclusion that no matter which circle you got, the number you get when you divide your circumference by the diameter will be the same. So although that's important, it's the definition of pi, or it's at least a definition of pi, it's not my favorite thing. It doesn't seem that exciting. Aside. This doesn't seem to have anything to do with pi. Select two random pairs of integers from 1 to 20. Okay. What's a number between 1 and 20?
7.
7 is a number between 1 and 20. And Ted, what's a number between 1 and 20?
12.
12. Okay. That's a pair of numbers. We need two more. What's a number between 1 and 20? Oh, I meant
Me?
my new friend. Yes, I don't remember your name though.
17.
17. And another number between 1 and 20. Somebody give me one.
2.
2. Okay? Well, we did it. Now what does it want us to do? Just following directions here. What fraction of them are relatively prime? Share no factor. So is there a prime number that divides both 7 and 12? No. Is there a prime number that divides both 17 and 2? No. So if it had been something like 6 and 12, then 2 would divide both of them. So I would have said yes. So what fraction of them? Well, that's easy. It's some number over 2. And the number of them is 0. So it's 0. So the computer's asking me what fraction. 0. Now what does it want me to do? Divide 6 by that number and take the square root. And it's not even a number. All right. Well, it's what it told me to do, so I did it. I don't really see what it's got to do with anything, but that didn't get us anywhere. We didn't get anything out of it. I hope the next slide's about pi, because we're supposed to be here talking about pi. So let me go on. All right, so another thing about pi is that it's a particular number. We said how it's defined, but we didn't say what number it is. Merely saying that if you take the circumference and divide it by the diameter, you get this number doesn't tell you how big it is. Maybe it's 25, maybe it's the square root of 2, I don't know. What number is it? And most people know, oh, I guess I said that it doesn't matter which circle we're talking about, that's why that's scaled there. Most people know that it starts 3.1 something, something, something. I myself have a counterable memory, so I'm trying to remember what comes next. It's either 4 or 7. This is another thing I should have looked up. Right here I am giving a talk on pi.
Considering we're doing talking to 18, I'm pretty sure the next number is 8.
Oh yeah, because pi day, and no, but I thought today wasn't. I'm so confused. It's times like this that I say to myself, how I wish I could recollect pi easily. That's a reminder of pi. The first word, how, has 3 letters. 3. I has 1 letter. Wish has 4. It was a 4. Aha. 3, 1, 4. How many letters? 1 again. 1, 2, 3, 4, 5. 1, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. All right. So that's a way to remember the first 8 digits in the decimal expansion of pi. And I personally think it's cool that an English sentence that reminds you says that it's going to remind you. I like that. That's cute. It's just cute. It's not my favorite thing about pi. It's another cute thing about pi. There are other mnemonics. There are mnemonics for remembering many more digits of pi than just this many. There are some of them that aren't exactly G-rated. There are all kinds of mnemonics out there that you could find. But this is my favorite mnemonic about pi, even if it's not my favorite thing about pi, because of the self-referentiality of it, how it talks about remembering the digits of pi. Oh no, not another one of these. So 10, it's going to take us a long time if I have to call you guys over and over and select 10 random pairs of integers from 1 to 100. What fraction of them are relatively prime? And what do you get? Okay, I have to pull this thing out. Let's use the computer to help us do this. So we want 10 random pairs of numbers. I've programmed the computer to do that for us. So I could show you the definition if you want. There's a program called Mathematica. When I say experiment 10, it's going to pick 10 random pairs of numbers between 1 and 100 and figure out how many of them are relatively prime, do the whole thing for us. So there, pick those numbers. 26 and 89 are relatively prime, 43 and 97 are. 62 and 2 aren't because they're both divisible by 2 and so on. So let's see, in the end, when it did it, it got 6 out of the 10 were relatively prime. So that means that 3/5 of them were relatively prime. And this weird command here is going to take 6 over, that percent sign means the 3/5 that came before, and take its square root. That's 3.16228. Wow, maybe this does have something to do with pi. Oh, I was pretty skeptical over here. But 3.16228, it's not pi. We just saw pi a minute ago. We know that's not it, but it's got the 3.1 part. Okay. Okay. Well, I did what it said. I picked 10 random pairs of numbers and computed 6, the square root of 6 over the fraction that were relatively prime. Back to the top. Another thing about pi, and you hear a lot of people talk about it, I've heard a lot of people talking about it when it was Pi Day and there were those newspaper articles about it, is that it's an irrational number. It's not obvious that it's an irrational number. It was obvious to me that it was going to be constant, that it's an irrational number. It took people a long time to prove. It was proved in 1761 by Lambert using continued fractions, I think is how he did it. But it's not obvious that it is, but now that it's been proved, we know that it is. And that means that the decimal expansion doesn't terminate. If you keep writing those digits out, you never get to a place where from there on out it's all zeros. In fact, you don't get to a place where from there on out it's any finite sequence repeated over and over and over again, although for a rational number, it is. If you take any rational number, take your cell phone number divided by your social security number. Eventually, that's going to be a repeating pattern over and over and over again because it's a rational number. So pi is an irrational number. It doesn't have that property. This is what the beginning of the decimal expansion looks like. And although we have formulas for figuring out what these digits are, and I'll show you some of those soon, we don't have a simple way to say, okay, well, from here on out, I know exactly what it's going to be, and there's no simple rule for it. You're not going to find a simple pattern in there. At least we don't have one that we know of yet. So that's something that people do seem to think is cool, and people always mention it. But it's really not an exciting thing. People mention it like, wow, pi is this number that doesn't have a terminating sequence or a repeating sequence. Yeah, well, there are lots of irrational numbers. In a certain sense, most numbers are irrational. There are a lot more irrational numbers than there are rational ones. If you really could pick a number from the number line, picking them all with equal probability, you'd pick an irrational one. We don't usually, because when we think about numbers, we tend to focus on rational ones. But there are lots of irrational numbers, so although it's useful to know that pi is an irrational number, it's hardly my favorite thing about it, because square root of 2 is an irrational number. 0.01, 001, 0001, 000 with more and more zeros, that's an irrational number. You know, it's not that exciting that it's an irrational number. 1,000 random pairs. Okay, I'm a little more optimistic this time, because we did it before, and it looked a little pi-like. So we're going to repeat the experiment now. With 1,000, so all I have to do is experiment 1,000. And it quickly picks out there 1,000. Some of them are relatively prime, some of them aren't. Out of them, 592 of them were relatively prime. So that gives us a fraction 74 over 125. And the square root of 6 over that is 3.18. No, I mean, it still starts 3.1. I don't see how it's much better than the other one, though. All right, whatever. I'll do it when the computer asks me to. I'm very obedient. All right, so those of you who were here at the beginning know that I have a hobby of keeping track of works of fiction with math in them. I have a webpage where I list thousands of works of what I call mathematical fiction. So famous books, movies, not so famous books, movies, plays, comic books, where a character is a mathematician or math is discussed, and there are some with pi in them. Those are things that I like about pi. The Life of Pi is a book, and in the book the character's name is Piscine, and the other kids at the school make fun of him, and so he changes his name to P instead of Piscine, and that's how the book came to be called Life of Pi. But that doesn't work. I was telling you that there's this pi-p confusion. In the movie, probably to avoid that whole thing, they don't mention that his name was Piscine, and so he changed it to pi. What they do is he becomes famous in his school because he stands up at the blackboard and he writes out digits of pi, and he fills up the entire blackboard with digits of pi that he's just getting from memory. So that's something with pi in it that's fictional. There's a movie called Pi, which is kind of freaky. How many of you have seen the movie Pi? Freaky, right? In the movie Pi, the number pi allows you to make predictions about the future, like about the stock market, and it's also got something to do with the names of God, and all these people are out to kill the mathematician who's figuring it out, and that's probably not my favorite thing about pi, because that movie makes me uncomfortable. But it's something, and it was interesting because the movie made a lot of money, even though it didn't cost a lot to make, so that's what people usually talk about. My favorite fictional thing about pi is in the book Contact by Carl Sagan, where in the decimal expansion of pi they find a hidden message. The hidden message starts with a sign to tell you that there's going to be a message there. What that sign is well, of course it's just digits, but there was a code. And in that code, the digits translate into a picture of a circle. So, in other words, there's this message in there, but the beginning of the message is a picture of a circle. A picture of a circle hidden in pi. That would be really cool. It would be like whoever made pi, as if there's someone or something that could make pi, did it in such a way that it comes from a circle and it's got a picture of a circle in it. That's really cool. It would certainly be my favorite thing about pi if it were true, but I think it's fictional. I ended up writing a short story based on a similar idea that appeared in a collection of short stories. In my short story, a grad student finds a hidden message in pi, but it's a message directed at that grad student. It starts with that student's name, and it says something to him directly. That's also a pretty cool idea if the message hidden in pi was for you. But in my story, first of all, it turns out to have been a prank played on him by other students. And second of all, the story goes on to point out that there is a mathematical theorem showing that any finite sequence will be found in almost any irrational number with probability 1, meaning that it probably is true that somewhere in the decimal expansion of pi there's a picture of a circle, and somewhere in the decimal expansion of square root of 2 is the script to the first episode of next year's Downton Abbey in ASCII code. It doesn't mean much, unfortunately. It just happens to be a property of infinity. So again, I'm not sure how much time you're expecting to fill up with things that aren't my favorite, but these are things that I like about pi but aren't my favorite things about pi. 10,000. Is the computer fast enough to do that for us without wasting our time? I think it is. So 10,000 of them. Yeah, it's already done. So out of the 10,000, 6,191 were, so the ratio is 6,191 over 10,000. And the square root of 6 over that is 3.11312. All right, this is, I think a lot of people who are knowledgeable about math would list this as their favorite thing. Pi is one of many famous constants in math. 0, 1, e, and I being the square root of -1, are other famous constants. And so for a lot of people, this formula, this true formula that combines all of them in an equality, is an amazing thing about pi. The fact that when you raise e, the number e from calculus, the one whose derivative is e, the derivative of e to the x is e to the x. When you raise that to the power pi times I, and you add 1 to it, you get 0. That is kind of amazing because it combines these numbers that come from different places. I think of e, for example, coming from calculus and derivatives. Pi comes from the geometry of circles. I is an algebraic thing, like you want to solve x squared plus 1. And 1 and 0 are just straight old-fashioned arithmetic. So it's kind of amazing that these numbers that come from such different places fit together this way. And so it is a neat thing, but I feel like I really understand how it connects to that definition I gave you before in terms of circles and circumference and diameter. Let me show you how it's actually not such a surprise to me. The thing is that if you raise e to the power it, where instead of pi you put some other real number t, that's the same thing as a point on a circle that's t units counterclockwise around the circle. So for example, let me freeze it somewhere. Freeze. This is supposed to be the complex plane. So these are real numbers this way and imaginary numbers this way. So that's the number 1 there. That's number -1 there. It's a unit circle. That's the number 1.5, the number 0.5. These are imaginary numbers. So that's number -0.5 I, or minus a half I. That's I up there. And any other number, any other point is a complex number with real part and imaginary part not equal to 0. And the thing is, if you raise e to the it, you're always going to end up with a point on this circle. And for that t, you end up with that point. That says something like 2.827. That's because that distance along the circle is 2.827. That's why it's that point. And so, if you pick the point that's over here, if you remember I said that was the number -1. That's the number -1. You raise e to the power of I times however long that is. So we have to figure out how long that is. Well, this has got a diameter of 2. So that's the diameter is 2. So the whole circle would be pi times that because of the definition. I don't even have to know what pi is. Just from the definition of pi, the whole circle would be 2 pi. So that top half of the circle is going to be pi. Yeah, that says 3.141. Yeah. Okay, so e to the I pi is minus 1. If you add 1 to it, you get 0. So it's the fact that minus 1 and 1 is 0, which isn't surprising, and the fact that that distance is pi, which again isn't surprising. That was the definition. So not my favorite thing. Okay, what number is that? Select how many? Is that a billion? Well, a billion numbers from 1 to 10 billion, I think is what it says. All right, I hope that I've got this saved. I did that before. Did I have it saved here? Yeah, there it is. That would actually take too long to do here. So some of them are relatively prime and some of them aren't. When I let it run through the whole thing, which took about an hour, 607,925,069 of them were relatively prime, and the square root of 6 over that fraction is 3.1415979. That's pretty nice. Seems, I mean, that's not the number pi, by the way. How many digits does that agree to? I've forgotten. 3.14159 parts, right? All right, pretty good. Seems like it's got something to do with pi, though. I'm not sure why it would. And that's kind of my point. Here's computing digits of pi. There are many formulas for figuring out what the digits of pi would be. First one I learned, I remember already, was this one called the Gregory-Leibniz series. Notice it's a sum of fractions, and the denominators are just the odd numbers. 1, 3, 5, 7, 9, 11, 13, and so on. The numerators are 4, 4, 4, 4, 4, 4, and 4. And then there's this alternating sign, minus, plus, minus, plus, minus, plus. You add that up in the sense of an infinite series, you get pi, or if you're not used to infinite series, that's the same as saying you decide how close you want to get to pi. Like let's say you want to get to 0.000001 of pi. Then there's a certain length that this can be, so that if you compute it out to that length or any more than that, then it will be that close to pi. So that's what it means to say that that adds up to pi. And I understand where this formula comes from. It's a little bit of calculus and a little bit of trig. So it comes from arctangents, and if you evaluate an arctangent function at nice, reasonable things, you often have a pi in your answer. So evaluating arctangent does give you pi's, and then it's got calculus in it, the Taylor series. So you have to differentiate the function, and the more you differentiate it, the more terms in this you find farther out terms from higher derivatives. So one bad thing about this formula is it's not very efficient. It takes a long time before you get an accurate approximation of pi. So people have figured out other formulas that are faster than this one, and since I don't care about speed, I guess that makes me a mathematician. I'm perfectly happy knowing that that adds up to pi without caring how quickly it does. But there is another formula of the many that you could find. For example, if you look at Wikipedia, you'll see lots of them. I'm not going to tell you about all the others. One other one that I wanted to mention, and when I told people I was giving this talk, another professor in the department said, oh, you know what you've got to mention? This same one. So this is a popular thing among mathematicians, the Bailey-Borwein-Plouffe, and it's not just because saying Plouffe is fun. The Bailey-Borwein-Plouffe formula has an interesting thing, which is that it lets you figure out any digit you want. Now, maybe you're thinking, well, they all let you figure out any digit you want, don't they? Well, this one lets you figure out any digit you want, but you have to figure out, if you want to figure out, let's say, the 100th digit, you first have to figure out the other 99 digits with that come before it. You can't just figure out about the 100th digit with the Gregory-Leibniz or any of the others. In fact, most people would have thought there wasn't a way to find, let's say, just the 10 trillionth digit by itself without anything else. But that's what this Plouffe formula does. It only works in certain bases, though. It works in base 16, which I think is cool, and that fit into my story, The Center of the Universe, the one about the person who finds the formula, the hidden message in pi, because base 16 is, of course, also something people use in computer science. And ASCII code is in base 16. So it's interesting that there's a way to get any individual digit you want in the base 16 expansion of pi. My favorite way to compute pi. Select n random pairs of integers from 1 to 10n, that is sounding familiar. Compute the fraction of them that are relatively prime, we've been doing that. Then take the limit as n goes to infinity of that. That's the same thing I was saying before, that if you choose a big enough n, you can get as close as you want to 6 over pi squared. Well, if the probability of that is 6 over pi squared, then you take 6 over it and take the square root, you get pi. So that's a way to compute pi. And it's certainly not a fast way to compute pi, but it is, you may disagree. Personally, it's my favorite thing about pi. That's my favorite thing about pi. One is that it's a way to compute pi that includes some randomness. Maybe I said that when I wrote this down. I'm not feeling as positive about it now because the experiments that I did today didn't work quite as interestingly as the ones I did practicing for this. That's the thing about a random method for computing pi. It's different every time. So every time if I ran those same things again for 10 pairs and then 100 pairs and then 1,000 pairs, I'd get different answers. There's something random about it. So that's kind of fun. That it's experimental and not always the same. But the thing that I especially like about it is that I don't understand it. I feel like I understand all the other things I told you. I kind of like mystery. I don't understand what pi has to do with whether two numbers are co-prime or not. There's primes and number theory, and there's pi, which has to do with circles, and I don't see the connection between them. I ask experts about it, I ask number theorists about it, and mostly what they do is they show me proofs that it's true. I know it's true. I know ways to prove that it's true. If you evaluate the Riemann zeta function at 2, for example, or if you make a lattice of the integer points in the plane and you figure out where a line first hits the lattice, those are different ways to prove this fact. It's not that I don't know that it's true or believe that it's true. It is, okay. I just don't understand why it's true, which is something different. It seems to me that there are a couple of possibilities for why this thing that has to do with whether numbers are relatively prime gives you a pi. One possibility is that it's just a coincidence. And that's what the experts usually end up saying to me when they're frustrated because I keep asking about it. Yeah, the number pi shows up there in circles. The same number pi shows up in this probability. So what? That doesn't mean anything, they say. Well, that would be a really interesting coincidence. There are lots of numbers it could be, right? If you compute a probability of something, the probability that if I drop a nail that it'll land in this box, not that one. If that happened to have a pi in it, that would be interesting. Or actually, that's got more to do with geometry, doesn't it? I'd understand that. This one I don't understand. Maybe it is a coincidence in the sense that I've, in preparing for this, saw that there's a formula for the probability of 3 randomly chosen numbers being relatively prime. And they've got a decimal expansion for it, and so far they don't see any connection between that and any of the other famous constants. Maybe it's just so weird and true that the same number pi happens to show up in a question about circles and a question about primes, but it seems so unlikely, of all the numbers it could be, that it would have a pi in it. Second possibility is that there's a hidden message in this from the being that created the number pi. Now, let's forget about that one. Third possibility is that there's an explanation, but nobody, not even the experts, seems to know it yet. Maybe there's something about the prime numbers that can be described in terms of circles and angles in radians, and the experts don't even know it yet. Maybe if we figured that out, we'd have a faster algorithm for finding which numbers are prime, or finding prime factorizations of really big numbers. That would be interesting and useful. And that's why that's my favorite thing about pi. I'm hoping that I've inspired somebody in this room to go figure it out, because I've tried and I haven't been able to find out this deep connection between circles and primes. And I wish you a happy belated Pi Day 2015. Thank you.